Hi, this is Mr. McGovern. This is the 7th and last video in the series on diffraction gratings and interference patterns, where we're looking at an NCEA problem, and the problem I'm looking at is 2019 question 3 from the Waves paper. So we have a laser sitting on a table, the beam goes through a diffraction grating, it spreads out, and you have this interference pattern of bright spots. They've also given us different coloured interference patterns where these different colours have gone through the same diffraction grating. You'll notice that red seems more spread out than the blue ones or the violet ones. So the first question is, describe using physics principles why violet maxima are closer together than the red maxima. So the first sort of key point here to notice in this question is they've said describe. So describe is an achieve level question. I'm happy just to give a short answer. It's not an explain question, so I'm not going to go into depth about path difference and all that. So describes is really easy. I can do that with just an equation. So I know that red wavelengths are longer and blue wavelengths are shorter, or blue or violet are shorter. We've got our formula for interference patterns. Rearrange it so we have sine theta on one side, and they're going through the same diffraction grating, so that's the same. However, the blue light has a shorter, smaller wavelength. So that means the angle, theta, is going to be smaller than it is if you were to use red, which has a longer wavelength. The second one says that the diffraction grating has 400 slits per millimeter. They show that that slip separation is 2.5 by 10 to the minus 6. Okay, so we have 400 slits per millimeter, which is 400,000 slits per meter. So I've just changed that into meters. Now what I'm going to do is I'm going to go 1 divided by that number. And the reason I do 1 divided by that number, look carefully at the units. So 400,000 slits per meter, but when I divide by that, it flips the units round. So I get the 2.5 by 10 to the minus 6 like they want, but look what's happened to the units. Now I've got meters per slit. So I've gone from slits per meter to meters per slit. So that's why I knew to divide it, because I wanted to flip those units around. That each slit is 2.5 by 10 to the minus 6 meters. I calculate the wavelength of the laser light. I'm going to use the same formula that I started with in part A, and I need to find the wavelength, so I'm going to divide both sides by n. They've given me n is 2 because we're looking between the center and the second order maxima. So I put all my numbers in, my angle, sine 20.9, and divide by 2. And that gives me 4.46 by 10 to the minus 7. I'm okay with that as my answer, but I'm just used to thinking of light in nanometers. So I'll put that into 446 nanometers. Both answers are considered correct. All right, explain the role of diffraction and interference in producing an interference pattern seen when light passes through a diffraction grating. So just explain diffraction gratings. So I'm just taking all this information from the videos I've already done and explaining it again, really. So when light passes through the slits of the diffraction grating, it spreads out. This is diffraction. The best way I can show this or describe this is with a little diagram. So I might draw this little diagram in my exam. That light that's diffracted and spread out, it interferes with each other from all the slits. And at different points on the screen, the light from each slit has had to travel different distances. Okay, and this is called path difference. It's a key word, so I've underlined it so the examiner can see that I know what I'm talking about. Now we describe what path difference does. If that path difference is a whole number of wavelengths, we get constructive interference. That's a bright spot. And if the path difference is a half number of wavelengths, then destructive interference, and we get a dark spot. So the last one, they've given us the wavelength of the green laser, and describe and explain what would be seen at point 28.6 degrees from the center. Calculation should accompany the discussion. Okay, so I'm going to go back into my formula again. I've been given the angle. I know what the D is, what the distance between the slits is. I know what the wavelength is. I don't know what n is. I don't know if it's a bright spot, like 1, 2, 3, 4. I don't know if it's a dark spot, like half, 1.5, 2.5, etc. So I don't know what n is. So let's find out what n is when we rearrange it. So I make n by itself and put the numbers in, and that gives me n equals 2.25. So this is going to be a dark spot because bright spots, let's start with diffraction grating. So we're using a diffraction grating, not a double slit. So in diffraction gratings, they have very, very well-defined bright spots when the path difference is a whole number of wavelengths, right? In between those bright spots, the rest is dark, and so we've got n equals 2.25. It's not a whole number, right? So if it was n equals 2, definitely bright spot. N equals 3, definitely bright spot. Anything in between that is going to be a dark spot, which is what we've got here. So that last one was an excellence. You needed the calculation. You needed to say that it was going to be a dark spot, and you really needed to talk about diffraction gratings having that very well-defined bright spot.